Let's look at an example of finding an orthogonal family of curves. So this time we're going to find the family orthogonal to y equals 1 over x plus a constant. So let's just get an idea of what our original family looks like. So y equals 1 over x plus a constant. So these are all going to be hyperbolas, but as we change the constant, the effect that has is shifting the hyperbolas back and forth. So again, we're looking for a family of graphs that are perpendicular to every one of these hyperbolas. Okay, and we have a plan. The plan is to find dy dx for the original family of curves. And one key thing about finding dy dx is that we have to eliminate the constant, right? Because we want to find dy dx so that it's a function only of x and y, right? So the constant shouldn't show up. Next, once we have dy dx just as a function of x and y, then we can switch to the orthogonal curves by taking the inverse, the negative reciprocal of the slope that we got when we found dy dx. And then the last step is just to solve the resulting differential equation. Okay, so let's, there are sort of two ways to go about getting or finding dy dx in a way so that we can eliminate c. One is to take a derivative first and worry about eliminating c later, or you can arrange the differential equation so that c will sort of naturally disappear when you take a derivative. So let's take a derivative here. We get dy dx equals x plus c to the minus second. We get a minus sign from the chain rule. Now here's where we need to eliminate c, right? We need to write dy dx in a way that's a function only of x and y. So we can solve this for c. So take reciprocals, 1 over y equals x plus c, and then solve for c. So c is 1 over y minus x. And we can put that into here. So dy dx equals minus x plus c, which is 1 over y minus x, all to the minus second. And something nice happens in this example. This doesn't always happen, but this x cancels that x. That's nice. And we get dy dx equals minus, looks like x squared when we simplify this. Okay. So that was, all right, that was step one in our plan. We started with an equation for our family, and we produced a differential equation that describes it. This is essentially a differential equation that tells you about the parallel slopes to the original family. So now we need to switch to the perpendicular slopes. And to do that, we do a negative reciprocal. So drop the minus sign, switch to 1 over y squared. So now this is the perpendicular equation. And then solve this to find the perpendicular curves. It's separable again. So y squared dy equals dx. Now we can integrate. On the left-hand side, we get 1 over 3 y cubed. On the right-hand side, we get just x plus a constant. Don't forget about the constant. I'm going to name the constant something different in just a minute so that we don't confuse it with the c in our original family. So multiply both sides by 3. So we get y cubed equals 3x plus 3c. And I'm going to name 3CA, just so that I have a different name for it. Okay, and then take cubed roots. So, y equals cubed root of 3x plus our constant. Okay, so now we can graph this. So let's call it f of x, just so that I'm sure it graphs right. So f of x is going to be 3x plus, I need a constant a first. So a is 1. Can't call it f, call it g of x is 3x plus a to the 1/3 power, so that's going to give us our root. And there it is. You can see that for this particular original graph, everywhere it intersects our new graph, the cubed root function, it is indeed perpendicular. And as we move the original one around, it stays perpendicular everywhere. And if we look at a new example for our perpendicular graph by changing a, that is also perpendicular to every one of these hyperbolas. And that's true for everywhere I put these sliders. These graphs are always perpendicular.